taking a look at some ideas in this video that have to do with work being done and the resulting change in kinetic energy rotational, or KE rot, and comparing that to our work done before and our regular kinetic energy stuff. So let's start here by taking a look at equation here. This is from chapter 9, where we have work done equals torque times theta. Okay, so this is similar to our work equals force. Our stand-in for force is torque, times our displacement, which will be our theta. Note that theta's got to be in radians. Okay, so let's go ahead and talk about that with that equation. All right, so we can compare to work equals force times displacement. So our rotational work here will be torque times theta. And one of our big ideas is that work is on equal footing with changes in energy. Okay, so if you have work being done, you're going to have some change in energy for the system. That's the big idea, is that if you have work, you got to look for changes in energy. More specifically, we've talked about work done by non-conservative forces equals the change in mechanical energy. And up until this point, mechanical energy has been made up of our gravitational potential energy, our regular old kinetic energy, and a little bit we haven't really done the problems yet, our potential energy of a spring, 1/2 kx squared. But now, because we have this work done by torques, we have energy that has to do with the fact that the object can spin, right? We know if we're going to be doing some work, okay, let's say we're doing some positive work on the system, and we're not going to have any changes with potential energy or regular kinetic energy, or our there's no springs in the problem. So if we apply a torque through some displacement and we make something start to spin up, like let's imagine we have a pivot point right there, and we push with a force here, and we make this thing spin, and we keep applying this force perpendicular, and we make it spin faster and faster and faster. Okay, well, the center of mass of this thing isn't going anywhere, so we're not going to have any change in this. We're not going to have any change in this. We're not going to have any springs or anything to do with that, so we need something else we need to account for, and that's something else. And there's a little bit of a derivation in the book on this, like a little bit of the math that is involved in it. But that shows up as rotational kinetic energy, which is 1/2 I omega squared. This looks a heck of a lot like this, so it should be pretty easy to remember. It's also on your equation sheet, but that rotational kinetic energy, or I call it KE rot, is just 1/2 I omega squared. There's that stand-in for mass that was in the previous ed puzzle, and then there's our angular speed squared. And that's it for KE rot. So now you can think about work done by non-conservative forces, okay, can cause a change in ME, but ME's now got a little bit more going on here. And if we specifically want to get into whether or not this is changing, we do need to think about this equation right up here to determine how much change in rotational kinetic energy we're going to get out of something. But that's something that can now show up in our mechanical energy. We've almost got everything now. There'll be one more addition here second semester with the electric potential energy ideas in terms of big energy ideas. But this is it for first semester. We've got all our different types of mechanical energy there. We'll talk about internal energy second semester as well in thermodynamics and fluids. So if you do some work, okay, some rotational work on a system, okay, you're going to make typically you're going to make the KE rotational go up. In fact, you have to, unless there's something else happens later in the problem to get rid of it, you're going to make KE rotational go up. So assuming you're keeping the mass in the same spot, like let's say this is the mass, it's all out here. It's like a big block stuck on a stick or something, you're pushing on it, and this is negligible mass, so that stays the same. The amount of torque you apply can increase the work being done, or you can apply it through a greater theta. So if you keep applying this force, this thing will just keep going faster and faster and faster, which makes sense because our KE rotational or KE rot will go up. Okay, because of all that positive work being done on there, we're going to make, if this stays the same, we're going to make omega go up. It goes faster and faster and faster. So there are some old ideas. Oh, and in terms of whether or not we're doing positive or negative work, it's the same thing that we had before with our FD stuff. If these two are like that, that's F and that's D, that's positive work. If that's F and that's D, if they're in opposite directions, that'll define to be negative work. This would make KE go up, right? This would make KE go down. Very similar thing here. If our force is in our direction that we are rotating, okay, so we're rotating that way, that's going to be positive work. If we already had it spinning and we applied a force in the other direction, okay, opposite the way it was spinning, that would be negative work, which would make the thing slow down or spin slower, so that we would decrease KE with negative work and make omega go down, assuming I stayed the same. All right, so there's just a quick little recap of some of those ideas with kinetic energy rotational.